already student Cesar Peralta from University of Antioquia in Colombia. So in this work, we investigate the so-called modified theories of gravity, also known as f of r theory, because they assume that the correct description of gravity is given by a nonlinear function f of r in the Jordan frame. As you may or may not know, upon a conformal transformation, we can go to the so-called Einstein frame, where the Lagrangian is described by an Einstein-Hilbert-like Lagrangian term, the Vitti scalar in this new metric, and the scalar field Lagrangian with a subject to a potential which is totally defined by this f of r function that we started with. I'll briefly remind you this procedure if you're not familiar with it in the next transparency. So in this work, we start with the following question. What would happen if we go the other way around? Namely, if we start in the Einstein frame with a given potential, let's say a plane phi squared potential, and then we ask what would be the corresponding f of r theory in the Jordan frame. And we end up with a surprising thermodynamic interpretation of the physical quantities in a different description, which is neither Einstein nor Jordan frame. So let me briefly remind you in the second transparency that we start, as usual, in the Jordan frame with a nonlinear function f of r, and upon a conformal transformation, which is given sorry, by f prime, the first derivative of f, and we end up at the end of the day with an Einstein Lagrangian, which is given by the Vitti scalar at this new metric, of course, and two terms that describe a scalar field subject to a potential that is totally defined by the function f that we started in the Jordan frame. So the question is, what if we start in the Einstein frame with a plane phi squared potential? Here, for the sake of completeness, we define the shift A, which will turn out not to be that important, and the cosmological constant defined, not that it is usually done, in the Einstein frame. At this moment, the cosmological constant is here just for the sake of completeness, but it will turn out to be a really important ingredient in the next transparency. So actually this question that we ask has already been answered in the literature. The reference is on the right hand side of the transparency. And it turns out that for this potential over here, we can write a parametric form for f and r. So if there is a parametric form, we can plot f as a function of r. So the picture that we have in mind is the following. We are in the Einstein frame, and the phi field is away from the bottom of its potential at a large value, for instance, and it will start going down the hill, but slowly. So if there is this slow roll conditions, then the system will go through an inflationary period in the Einstein frame, and of course, there will be a corresponding inflationary behavior in the Jordan frame as well. And then, when the system goes close to the bottom of its potential, it starts to oscillate around it, and then it will eventually stop at the bottom of its potential because of the friction caused by the expansion of the universe. So in the first stage, the system is slowly going down the hill. If we picture f as a function of r, the system will be in the first branch over here, which is this curve, almost linear, but it's not, really close to the x-axis over here. Then it will briefly stop at the other side of its potential, which is this cusp over here, and then it will go all the way the opposite direction. It is the first oscillation of the phi field, and then it will oscillate around here in the third branch. So this second branch here is where the second derivative of f is negative. It's known to be unstable. But here, this phase is only is temporary. So this instability is not actually harmful to the model. And at the end of the day, the system will oscillate around the bottom of its potential in the Einstein description. In the Jordan description, it will behave as general relativity because this curve over here is almost linear. And if we change the value of lambda, the second branch over here just disappears above a given value. If we change a, it's just a change of scale, so this is not important right now. So this, as I said, has already been done. And the new piece of information is if we identify lambda, the cosmological constant, as an effective temperature, f of r as an effective pressure, and Ricci scalar r as Gibbs free energy. And why do we do that? We do that because if we plot f as a function of r and lambda, that's the picture that we have. In this region over here is the unstable region where the second derivative of f is negative. And we, upon this identification, we have this function over here. It's just a rotation redefinition of the axis. And this is exactly the same thing that we have in thermodynamics. We have this region over here where with a higher value for the Gibbs energy, it's the unstable region, which is exactly this one that we have over here. Right? And above a given temperature, which is the cosmological constant, there is no instabilities in the system at all. So if we have Gibbs energy, we have pressure, and have temperature, we can define the effective volume of the system. Let me just point out, I would like to stress that this is not an effective curvature fluid that comes from playing around with the terms in the modified Einstein equations in the Jordan frame, and neither it is a fluid interpretation of the scalar field phi in the Einstein frame. This is a new interpretation. This is not Jordan. This is not Einstein frame. This is something new. So I can plot pressure as a function of the volume for this new uh, interpretation, and we have almost exactly a van der Waal gas. It's not the same analytical expression, but the main features are all here. Namely, we have above a critical value of the temperature, we have an ideal gas behavior, and below this critical temperature, we are able to plot the binodal and spinodal lines. And let me remind you that the region between the binodal and spinodal lines is the region of metastability, means that like a supercooled gas, for instance, and the region below the spinodal line is the region of instability, where fluctuations would grow. So if you go back to the picture that we had in mind, the Einstein frame, the field phi slowly rolling down the hill, then that would correspond to the van der Waal gas with a really large volume, and that would correspond to a metastable region because this would be the region between the two lines, right? And thinking of vanishing cosmological constants, for instance, that would correspond to this lower gray line over here, right? So the system starts in a metastable state, which is exactly what happens. Inflation doesn't last forever. And then it eventually crosses the spinodal line. That's the region where the system is unstable, which corresponds to this region over here, where the second derivative of f is negative. And it then crosses to the other side, crosses the spinodal line again, and at the end of the day, it oscillates around this gray dot over here. So in this picture here, we have a transition from gas to a liquid, right? And in the Einstein frame, for instance, we have the same qualitative transition. We have initially something that behaved like a vacuum because the low conditions hold, and then at the end of the day, we'll have something that behaves like dust, as a scalar field oscillating around the bottom of its potential. And in the Jordan frame, we had initially a nonlinear function of r as a Lagrangian. We have a modified theory of gravity in the beginning, and at the end of the day, we have something that is linear in r. So we have general relativity at the end of the day. So this change, this qualitative change in the behavior, either in the Jordan frame or in the Einstein frame, is seen here in a new description. Of course, we can plot the entropy as a function of temperature, as a function of pressure, and we can map these lines onto this picture over here, which is exactly what we would expect if we remind ourselves from catastrophe theory. That's exactly the picture that we have in the first order phase transition. And of course, we can also plot specific heat at constant pressure, for instance, which is divergent for lower values of temperature and which does not diverge for larger values of temperature as expected. And the really interesting piece of information is this one. We can we can define the sound speed squared of this van der Waals gas. So it is defined as P dot over rho dot, where P is the pressure as the f of r, dot is the time derivative, and rho dot in the denominator is the energy density, the time derivative of the energy density. So P dot over V dot is the sound speed squared of this van der Waals gas, and it's negative if the temperature is low enough, and it's negative exactly where F double prime is negative. So those are the same instabilities that we were already aware of in the beginning. So right now we are pursuing characteristics of this instability region. Let me just remind you that usually anyone that studies modified theories of gravity would disregard theory with F double prime negative because it is unstable and no one wants instabilities in your theory. But here, it doesn't harm the theory at all because it's really transient behavior. Just in the first oscillation, the system really goes really quickly through this region, and after that, it's stable again. So we are looking for characteristic length, for characteristic amplitude growth of these perturbations to put some constraints on this theory. Thank you very much.